You know, we start with a cavity, we did an ABCD of it, and we used the ABCD law, we figured out the spatial mode. As we talked about a lot, what the spatial modes look like. And then Deb Beep talked about the Hermite Gaussian modes, so you get these various higher order things going on in there. So, you know, a fundamental mode might look like that. The 0-1 mode is going to kind of look like this, if I shine it on the wall and so forth. And you get these higher and higher things. And the basic idea is, usually you take if I have some gain in a material, you notice that the beam is very small, the mode volume is very small, and there's gain outside of that mode volume, other modes will light up. So the way you typically see multi-modes is by having a large mode volume. The classic is an old neodymium YAG laser, and it would be a cylinder of YAG, and this might be 5 millimeters in diameter. And they shine light on it from the sides, so the whole thing is active. And as you learn, you know, the mode spot size is on the order of 1 millimeter or less. And so there's a lot of gain here. And so what happens is, yeah, the 0 mode goes on, but all these other modes. So you get this big multi-mode blob coming up. And so if you just want lots of power, that's great. You can get this big multi-mode thing. All these modes are there. You've got the TE2020 mode and so forth going. The problem is you don't have any spatial coherence. And this is because every one of these modes has a different frequency. That's what we'll talk about today. Every one has different frequency. So when I look at the phase front here, it's chaotic and it's rapidly changing. So if I want to take this laser beam, which is a big honking laser beam with a lot of power in it, and I want to do interferometry or something like that, it's not going to work because it's an incoherent source when I get lots of modes. You need a single mode for coherence. So we'll talk about that. Why are these all frequencies different? Let me just ask one quick question. Let's look at the 0-1 mode. You know, I shine it on the wall, it looks like this. I look at the side, it's actually two beams kind of traveling along. One is polarized up, one is down. Yeah, they're orthogonal polarized. I got this 0-1 mode going. I run it through a lens. What happens? What does it look like at the focus? What happens when I take these two beams, they're cruising along, I run it through a lens, they focus, and eventually I've got two beams over here, side by side. What's it look like right there? Any guess? Well, the answer is it looks just like that. This shape is preserved everywhere. So what happens is these modes focus down, and literally never cross. Now, how can that be? How can light bend? You know, light goes in a straight line. So what's happening? It's very interesting in this case because the polarizations are different. One is polarized up, one is polarized down. As they start to cross, of course, they annihilate each other. But what happens is there's a very strong Z component of polarization here. So normally this is a transverse electric field, but as you focus the 0-1 down, the polarization, each of these kind of swings to Z and then swings around to the other side. So if you want to get a nice longitudinal electric field, that's where a 0-1 mode might be useful. And you focus it down. And you know, it does seem kind of magic. How could it always be like this? How could there always be a gap and yet the light crosses the path? Well, it's doing it by going out of the transverse domain into the longitudinal and then back down like that. So it does work out. You can prove this using the divergence law, Maxwell's equations. So I just want to throw that out. Anyway, today's lecture is about frequency. So let's look at that. So I'm going to look at a cavity, and let's just do plane mirrors. Doesn't much matter. So I've got two mirrors separated by some distance d, and I want to shine a plane wave on it. And what we're going to find is that a plane wave goes in, it bounces, comes back, it bounces, it bounces, it bounces, and so forth. It's going back and forth. And as it propagates, it accumulates from one point to another the phase of its wave vector k times d. Remember, k was the wave vector, radians per centimeter. So 2 pi over lambda. How many rads does it take per going unit length? So going from here to here, it accumulates kd of phase. And it bounces back, it comes back another 2d of phase. And here's where things get interesting. Going from here and back, it's accumulated 2 kd of phase. the critical thing to be in resonance is that the phase here must equal the phase here. So KD is of course some integer number, or it's going to be some number times pi. And so we want an integer number there. If it's an integer number, or times 2 pi in this case, then it's in phase. So we're going to look for a cavity where the wave propagates there and comes back, and after one round trip, it's back in phase with itself. And if it's in phase with itself, then it can do it again and again, and every round trip it just keeps coming back and building up, and it's always in phase. If it's slightly out of phase, what's going to happen is that error is going to accumulate, and after so many bounces, it gets longer and longer, proof that it's exactly out of phase with someone earlier, and it leads to cancellation. So if we don't have these things perfectly in phase on a round trip, you don't get a buildup. And so that's what the resonance is all about. That's what that happens in a resonance in an organ pipe in this room. You know, we get resonances. And in the cavity the same way. You've got to have this situation here where this equals 2 pi times some integer number. Now here's, today's lecture is crazy because what's our integer number? We're going to use an integer number of Q. And you're going to find we beat this poor number to death today. So this is not the same Q we talked about the other day. We had Q of Z, wonderful thing for spatial modes. This is just an integer. This question?
So is that the quality factor that you're going to go over?
Well, we're going to get to a quality, we're going to get to the third Q later today. Yeah. So
my question is, so if the beam is not in phase, or like if the wave is not in phase, then does that pretty much die off in the end?
yeah, it rapidly dies off because, you know, eventually, you know, this will be going forward, and after a few round trips, it's out of phase. So if this is out of phase with that, they cancel.
Oh, but then we're not projecting the wave like so that it doesn't come back to.
Oh, I drew this. This is maybe a time. They're going back and forth on top of each other. So each of these reflections piles up.
Okay.
Yeah, it's not like this is on the bottom of the room and that's the top of the room.
Okay.
This is more meant just kind of a symbolic thing.
But then if it is in phase, then does you say accumulate, so it's gonna like, you know, increase in energy?
Yes, it will. Yeah, if we keep feeding it, we'll get to that. But if I keep putting energy in and it keeps running back in phase, what's happened is the energy builds up dramatically in here. You see this in an RLC circuit. You know, you take a very weak signal off an antenna, feed it into an RLC circuit, you build up a big voltage, you store energy in that.
Right.
So it's the same idea.
Okay.
Yeah. So this resonance is a very common phenomenon. Anyway, we're going to see 3 Qs. So this is used Q. The reason we do this is we call these are called the TEM NM modes. Actually, they're MN, but I'm from New Mexico, so it's always NM in my class. So I'm not from Minnesota. You know, so they have the TEM, and so this would be, you know, the number of lobes. So this is the TEM 00. This is the TEM 01, or maybe it's a 10, you know, something like that. So that tells you what the spatial modes are. We finally say, well, but we have possibility. I might have 2 pi 60 or 2 pi 61 as a resonance mode. So we also have how many wavelengths are inside the cavity. And so we make that the third integer. So NMQ is why we use Q. So it's an integer, and it goes with this notation where we're describing the spatial mode. So it's got this that many transverse lobes, that many transverse lobes in the y direction, that many transverse lobes in the z direction. So that's why I'm making an excuse why you're seeing Q again. And as you said, we're going to have Q still ahead. We get to the Q factor. So there's lots of Qs today. But anyway, here's our resonance condition. You know, so we have to satisfy that. Okay, that's pretty easy to do. Now, we often do this in terms of wavelength. And let's see, I'm going all over the place on the board here. So 2D times K equals 2 pi Q. K equals omega over C, or it equals 2 pi over lambda. So I can replace K with 2 pi over lambda. And what you get out of this is D. I'll solve for D. Where's D? Yeah, there's D. Okay. I get D is going to be equal to Q times lambda over 2. And so I only do this to show you that effectively our resonant cavity is, as you expect, some integer number of wavelengths on a round trip. The half paths be an integer number of half wavelengths. So you have to fit wavelengths into this box. So standard box, you give me a box like that, my first resonance is going to be that. My second resonance will look like this, and the third. So there's going to be discrete, very discrete frequencies and wavelengths which fit in this resonator. And they just have to satisfy this condition, which is the same as that condition. But K is kind of a number. This at least is something tangible we can relate to. Does that make sense? So we're just, just making a resonance picture. You've heard of, half wavelength antennas. It's just this standard kind of stuff. Let's look at a YAG laser just for fun. Let's say I've got a YAG laser. Just to give you some idea of what numbers we're talking about here. I've got a YAG laser. It's 1 meter long. It's got a 10 centimeter crystal of YAG in it. That has an index of 1.86. It's got a wavelength of 1.06 microns. So what's Q for this cavity? So we know that we've got 90 centimeters of air. So I've got Q is going to be equal to 90 centimeters divided by 1.06 over 2. So this is going to be 1.06 microns over 2. So this is lambda over 2. And then I'm going to have plus 10 centimeters of 1.06 over 2 times 1.86. I divide the wavelength by the index of refraction when I'm in an index material. So here's free air. The wavelength is 532. Inside the material, it's 532 divided by 1.86, the index of refraction. So the wavelengths get shorter in the material. And so you grind that through. This is microns again. Anyway, and I got a number like 2,047,737. So just to give you some sense, we're not talking about cavities where I've got, 1, 2, 3, or 4 lobes. Your typical laser cavity has millions of waves between the mirrors. Millions of waves. Yeah.
Sorry, what's a YAG laser?
Yeah. Neodymium. YAG is yttrium aluminum garnet. It's a crystal. Neodymium is a transition metal. No, it's not. I'm sorry. It's a rare earth, and it's got a nice transition which is used for making a laser at 1.06 microns. So it's a classic solid-state laser. If you've ever seen a green laser pointer, that is a YAG laser, which is frequency doubled to give you the green light. So you've probably played with one. It's just kind of the workhorse laser of the industry. It works very well. People love it. It's one of the first lasers ever found and still widely used. But I just want to give you a number. We're talking about a lot of waves in a cavity. So whether it's 737 or 736, things change a lot. Okay, now I want to introduce a new term. So we talk about these cavities, and I want to write it now in terms of frequency instead of wavelength. So again, we've got 2d times k equals some integer times 2 pi. I know that k equals omega over c. That equals 2 pi nu over c. So I'm going to substitute that in. Yeah?
I just want to clarify, what's is 90 part of the length of the cavity?
Oh yeah, 90 centimeters and 10 centimeters. Yeah.
Yeah, just making sure that was
Yeah. So, good question. I'll talk about this more later, but basically, we have a lot of wavelengths today, lambdas, and we have lots of Cs. And if we're in a vacuum, wavelength is just C over nu. But if we're in an index of refraction, you always divide the wavelength by n. Or, equivalently, you divide C by n. But if we're in index of refraction, all our formulas change with a factor of n. And where do you put it in? You divide C by n. You divide lambda by n, and your formulas work. So here I divide lambda by n, and that works. So the index of refraction is common. We're assuming vacuum for a lot of this stuff, but if you're not in vacuum, you just throw in the factor of n. The book is very good about this. His formulas all have n, so it's all taken care of. I'm very sloppy about this. So I just implicitly assume you all get it. let me know. Okay, anyway, so I've got this. And I want to solve for, I'm going to substitute that into there and solve for nu. I want to describe this in terms of frequency. When you do that, you find that nu equals this integer q again times c over 2d. Okay, c over 2d. This is a very important number. C over 2L, C over 2D. This is called the free spectral range. And you're going to see this term a lot. So we're going to introduce a lot of terms today. And the FSR, the free spectral range, is one of them. It's C over 2D. What the heck's it mean? D is the distance between the mirrors. It's clearly a frequency. And the actual frequency we're lasing at is some integer number, like 2 million, times that. So if I were to look at the resonant frequencies of this cavity, I've got this cavity, it's 2 mirrors separated by a distance d. As I can go to new board. What we'll find is we'll get a resonance every half wavelength, or every time we get another integer number of wavelengths in there, but that's kind of strange to plot. So if I plot it in terms of frequency, I just say, here's my allowed modes. And I'm going to plot it as a function of nu. I'm going to find every free spectral range. Every time I go C over 2L in frequency, I get an allowed mode. So I'm going to have an allowed mode. So here's my first lambda. Here's one that's lambda over 2, lambda over 3, lambda over 4. The frequency goes up linearly. This goes on forever. So here I am at 2 million, 2 million and 1, 2 million, so forth. And the distance between these two, any allowed mode, is called the free spectral range. So it's the range between these allowed frequencies. Now to put some numbers to it, let's say we have a 1 meter cavity. So here's a mirror, this is 1 meter. So FSR for this is C over 2L. So I use centimeters, use whatever you want. So in my case, it'd be 3 times 10 to the 10 divided by 200. So it's going to be 150 megahertz. So I've got this pair of mirrors separated by a meter, whatever that is. And it's going to have resonances, and lots of them, but they're going to be discrete, sharp resonances every 150 megahertz. So when I put my YAG or whatever in there, it's going to have to laze on this one, or maybe both, but it's not going to laze in between. There's no way I can build up any radiation in that cavity at that frequency. So as soon as I put mirrors down and define a position, I suddenly have discrete frequencies at which the laser must operate. And it has no choice. It has to operate at that frequency because that's the only place the modes are. And they're separated by the FSR. So what's the FSR of this cavity? C over 2L. Put the numbers in. If it's full of glass, if this whole thing is full of glass and it's got an index, say 1.5, I would put an n down there. I divide by n, and my free spectral range would be whatever it would be, smaller. Yes?
So the L, is that in units of centimeters?
It's whatever you choose for units of C, make the same units.
Oh, okay.
So you want to do meters or I don't care what just make sure your units are consistent.
Okay.
That's all you have to worry about. So most people use meters. I use centimeters. Whatever you like. Let's try a diode laser. So let's take a diode laser. Let's take gallium arsenide. It's got an index of 3.6, and a typical laser might be 200 microns. 200 microns, yes, that's just a little bit bigger than a hair. So what's the FSR on that? Okay, it's 3 times 10 to the 10 divided by 2 times 200 microns, that's 200 times 10 to the minus 4 centimeters, and then times the index of fraction, 3.6. And you grind that through, and what did I get? I got 208 gigahertz. So this poor little laser is only going to operate on certain discrete frequencies, and they're separated by 208 gigahertz. So When it lasers, it's on this mode or that mode or maybe both, but nothing in between. So that's one of the first things you see about a laser. When you turn a laser on and you look at its spectrum, you don't see, what you'll see typically, this can be wavelength or frequency, you'll see a number of specific lines, and the spacing between the line is going to be the FSR. So it's going to be discretes, a bunch of discretes. Now, someone asked me once, well, you know, what if the gain doesn't match this? So let's say I take my YAG laser and I put it in this cavity, and the YAG laser only has gain, say, from here to here. It's not going to laser. That's all there's to it. But in fact, in truth, most laser systems have fairly broad range of gain. They typically, you know, a gas because of Doppler broadening has at least a gigahertz. And so a gigahertz, you know, and here I've got a cavity which has 100 megahertz FSR, I'll have no trouble. The gigahertz will span this, and what's likely to happen is I'll have lasing on 5 or 6 of these modes. So there'll be specific modes light up, but that's because the gain expands over them. Gallium arsenide has a huge gain bandwidth. It'll have no trouble overlapping a couple of these modes, even though they're 200 gigahertz apart, and finding one to operate on. So it's not a big issue, but typically you say, wow, these are discrete lines here. The gain, we'll find the gain has always got some sort of continuous spread, and so it's just so long as that spread covers some of these modes, the thing lights up. So, but the actual frequency of the laser, the specific frequency of the laser, is determined by this cavity. You know, the general frequency, this is bad. The general wavelength of laser is set by the laser. It's going to work at 1.05 microns. Okay, but which exact frequency it works at depends on where I put this cavity mode. And I can actually change that, and I can tune the laser over some bit. But the actual frequency is defined by that within this range. The laser, the gain medium says, okay, I'm going to laser this rough area. The cavity picks it specifically. So we've got, what else? We've got FSR. So here's another one we got to remember. So FSR is C over 2L. Remember that term. Onward. More definitions here. Now, we got this cavity, and the way we make lasers is we make the mirrors which are partially reflective. So instead of having perfect mirrors, you'll have a mirror and it's going to have some reflectivity. And so this adds yet another degree of confusion, because last week we were talking about R1 and R2, and we were talking about the curvature of the mirror, right? Now on the same mirror, I'm going to give it an R1 and R2, which are the reflectivity. So you have to look at these drawings and say, is he talking about reflection or curvature? You know, so today it's reflectivity. Today is just complete recycling of every term you've seen with new definitions. It's really awkward. But the way we make a laser typically is we make these reflectivities, and we'll make one of them, let's say one, we'll try to make it approximately 100%. You know, 99.5% is a fairly easy mirror to get. And another one, so let's say this is our high reflector. We call this the high reflector. We want all the energy to be reflected. This one will make partially transmitting. We might make it a 90% reflector, an 80%, or 93%. And so the light comes in, hits it, some leaks out, the rest is recycled and comes back. And so this is where we get our output. Here's how we generate light, and we have these mirrors, but we let some of the light leak out, and that's where we get a useful output of the laser. So it's just by very controlled predicting how much we let leak through. Okay, so when we have a cavity which has partial reflectivity, these sharp lines become a little softer. And in fact, they start to broaden out a bit. So we're going to find, if you look very closely at the reflectivity, if you have very sharp, you're very high, and if reflectivity is 100%, you get a sharp line. And as the reflectivity starts to soften, these transmissions broaden out a bit. And it becomes a little bit less. And the reason, why is that? It's because light doesn't spend as much time in here. If I've got a 10% coupler, it's only going to make 10 passes before it finally gets out. It only has 10 chances to accumulate enough phase area to cancel. And so, you know, I can be a little bit off and probably not affect much. And so that's why these things broaden a bit. So we want to look at what's the bandwidth. What's the bandwidth of one of these transitions? Okay, so way to do it, you basically do a series. You look at something like that. You define your mirrors. You're separated by some distance. You define a reflectivity at each one. We're going to use electric fields. Capital R usually corresponds to intensity. So when you say capital R, I've got I1, and it comes in and it gets reflected, and so I've got I1R reflected back in intensity. We're going to use electric fields to figure out the fields because we have to do superposition here. So we're going to define this as gamma, gamma 1, and gamma 2. And here you've got E transmitted equals E incident times gamma. So gamma is, oh, I'm sorry, that's E reflected. So gamma is my reflection for the electric field, not the intensity. If you square it, it's the intensity reflection. And let's imagine we bring some beam in. We've got some little beam coming along, and it's got an electric field, and it's got a K vector, and it's incident on this thing. And some of it reflects away, but some transmits. And this transmitted stuff goes in, and it's this, and some transmits, and some reflects. And some transmits, and some reflects. And it's just going to do this, forever. And so what we want to do is add up all the terms in either the reflection or the transmission and see what this adds up to. And so if you were to look at this term here, the transmission, how much came through here? Well, I had a field coming in here, so I've got some E naught. It transmitted through this first one. I'll just call that little T1. It went to here, so I've got E to the J KD, and it transmitted through here. So I've got a T2. So there's my field here with respect to E naught starting there. Its amplitude's been reduced by T1, T2, and it picked up phase. Now, this one bounced here, came back, and now it transmits out. So this one looks like E naught. It also did a transmission in, transmission out, so I'll just put a T1, T2. But it also had a reflection 1 and a reflection 2. So it's got a gamma 1, gamma 2, and then its phase is E to the 3 JKD. And then this one bounced, came back, and this one, of course, looks like the same thing. E naught, T1, T2, gamma 1 squared, gamma 2 squared, E to the 5 KD, and so forth. And so you can do this all day long. And what's my transmitted field? And I'm sorry, this is very sloppy, but you just add these all together, and that's what's out here. That's what transmits. And so we can simply write a series solution, which says, well, the transmitted field is just the component of all those. And when you do it carefully, what you get, you're going to get something of the form, E transmitted is going to be T1, T2 times 1 plus gamma 1, gamma 2, E to the J, K, let's do it, E to the 2 J, KD, whatever. I guess I'll say 2 J, KD, plus gamma 1 squared, gamma 2 squared, E to the 4 J, KD, plus and so forth. I'm missing a JKD out here. Infinite series. It's power series. You can easily sum it up. So you do the sum. It's easy to do. You recognize that 1 minus gamma 1 squared equals T1, and gamma 1 squared equals R1. So this is my amplitude. This is my intensity reflectivity. Question?
Where did E naught go? Or is it just
Oh, E naught should be here. E naught should be in here too. Yeah. It's all going to normalize out. So what I do is I sum it up, and at the end of the day, you can say, okay, my transmitted intensity divided by my incident intensity. That's where E naught went. And you pull all these terms together, is 1 minus R1 times 1 minus R2 divided by 1 minus R1 R2 square root squared plus 4 square root of R1 R2 sine squared theta. And theta equals KD. So you can see if KD is an integer number, pi, then sine of that is 0, and we get a nice expression here. And well, let's look at that. If let's say we're on resonance, you know, like we were talking about, and so KD equals some integer number pi, so the sine term equals 0, and let's let R1 equal R2. Let's just have a nice balanced cavity. So R1 equals R2, theta equals 2 pi times Q. This becomes 1 minus R squared over 1 minus R squared equals 1. So my transmission is 1. And I get perfect transmission in this thing when I'm right on resonance. And as I get off resonance, this term starts to grow, and you can see the amplitude starts to fall. So as I go off resonance, I'm no longer, you know, I'm no longer on my mode here. As I'm getting away from my mode, we start to get a little less transmission. And this describes how this transmission goes as a function of the reflectivity of the mirrors. So you can put in various R's here and compute how, you know, you're always going to have maximum transmission at resonance, but how fat is it? You know, how broad is this curve? How sharp is it? So by adjusting my reflectivities and stuff, as I go off resonance, I'll see rapidly how fast it goes. So this fully describes the transmission of the cavity as a function of reflectivities. Just to illustrate.
Wait, can you repeat that last part, please? As a function
Of the reflectivity.
the first part of that sentence.
Well, what this will do, if you plot this equation, maybe it's fun to do. Plot this equation and then choose various values of R and let theta scan from 0 from pi to pi. And you'll find for very high value, for R 99.9, you're going to find your curve looks like this. And when you make R 98, it's going to look like this. When you make R 95, it's going to look like this. When you make R 50%, it's going to look more like this. You know, so you're going to find that as you increase the reflectivity, you increase the selectivity of your cavity. It becomes much sharper in terms of its spectral width. And that's where we want to go. We want to figure out what the half width is. I wanted to illustrate, though, how this works. It is kind of, seems counterintuitive to some extent. Let's imagine I take a 99.9% mirror, a really good high reflector. I've got 1 watt coming along here. I'm going to put a 99.9% reflector right there. And I want to see what's coming through here. So, you know, I'm going to have 999 milliwatts bouncing back. I'm going to have 1 milliwatt coming through. No big deal. Now, I take a second 99.9% mirror, I put it at just the right place, and bang, I have 1 watt coming through. So I'm going to put this little guy in this 1 milliwatt beam, and the next thing I know, I have total transmission. And that just seems, how could that possibly be? Now, I had to put it at exactly the right point, so I hit resonance. So I've got an integer number of waves here. And what's going to happen is that 1 milliwatt is going to come in, and it's going to be trapped. And it's going to go reflecting back, and while it's reflecting back, more power is coming in. So we're slowly building up power inside this thing. And as this power builds up and up and up, we start to get interference, and positive things happen. So when it finally gets settled, when it finally reaches equilibrium, I will have 1,000 watts moving this way. 1,000 watts hit that mirror. 1 watt, or is it 100 watts? It's 1,000 watts, yeah. 1/10% of it gets through, so that's 1 watt. 999 goes back. It sees that, and 0.999 of it transmits out, but it turns out that's exactly out of phase with the reflection caused by my incident beam. And so this reflection, I still see this beam comes in, still sees this mirror, it reflects, but the reflection is exactly equal and opposite to the transmission of this one. And so these two are just out of phase. So this very intense 999 cancels that reflection. And so now I get 1 watt coming back in. So this watt enters, so I get 990 going that way, 1,000 going that way, Here, nothing cancels, so it all just leaks out. So what's happening is I've got a huge buildup of energy. I've got this energy storage here. You mentioned a minute ago, got a little field coming in. It builds up huge inside the resonator. That's energy storage, and then comes out. So when I first put this mirror here, I got a milliwatt coming through. When I put the second mirror there, it didn't just happen. I've got to have a buildup. So it's going to take a while for this to build up. Then so it's going to, that's called the photon lifetime. We'll talk about that. And if I turn this suddenly off, I will find my power decays. It's like an RC circuit. So we do have to build the storage up. But once you got it stored, it goes a long time. So that's kind of the physics of what's going on. But anyway, what's the half width of this? So if I want to know what's the half width, I think I'll spare you the math, but I look at this equation and I look and say, well, you know, when I'm right at resonance, this term equals 0. But when this term equals this term, then I've doubled the denominator. I've dropped it by half. And so I look for the condition. The half width point is going to occur when 1 minus the square root of R1, R2 squared is equal to 4 times the square root of R1, R2 sine squared theta. And so that's when I know I'm at my half power point, and I can solve that for theta, which is my phase term, KD, and figure out where my half power points are in terms of these R's and so forth. So we can do that. It's pretty, you know, it's just algebra basically. And what you get when you do that, you know, basically I'm going to look for sine squared of theta equals, what do we got? 1 minus the square root of R1, R2 squared over 4 square root of R1, R2. And I'm going to say, well, you know, this is KD, and that's approximately 2 pi Q plus some delta, you know, some delta K kind of thing. So 2 pi Q is 0. The sine of that's 0. So this is basically becomes sine squared of my delta K because I'm right near resonance. And so we expand all that kind of stuff out. What you get when you're all done with this thing is that, I'm just going to write the answer down. You get the delta nu equals C over 2D. Recognize that? What is it? FSR, good. Times, that should just be instinctive. I can call you 4 a.m. in the morning. What's C over 2D? Oh, FSR. Just what do you think? 1 minus R1, R2 to the 1/2 over pi R1, R2 to the 1/4. Okay, there's our half width. Just kind of a strange formula, but you have it. So you can see by adjusting the reflectivities, I can make this thing sharper and sharper or broader and broader as I wish. So now we go to our third Q. So if you've ever taken a resonant frequency, if you ever built an RLC circuit or something like that, you always characterize this thing by the Q factor. And the Q factor is called the quality factor. And at least it's a capital Q. It's not the small q. But it's defined as basically, well, there's several definitions, but in frequency it's nu over delta nu. So you've got this resonance. It's happening at some frequency nu, and it's got some half width delta nu. And so the Q factor is what's the ratio of its resonant frequency to its half width. So for a good RLC circuit, you know, Q of 100 is pretty good. But we're going to do the same thing here. We're going to define that for a laser mode. So we know the frequency and we know the half width. So you can figure that out pretty quickly. You know, nu is just C over lambda. And so Q is just going to be C over lambda divided by this thing, you know, C over 2D times 1 minus all this crap. Okay, so we got all this stuff here. And, you know, massaged a bit. You end up with a cavity Q. Here's our final simple formula. 2 pi d, depends on the length of the cavity, over lambda, R1, R2 to the 1/4 over 1 minus R1, R2 to the 1/2. So there's the Q of a cavity. Plug some numbers in. I think let's just try. I put some numbers here. Let's say our cavity has a 99.8 reflector here. We go 1 meter, and we put a 95% mirror here. You plug the numbers in, you get a Q equals, it's a big number here, 3.72 times 10 to the 8th. So these Qs are pretty impressive. So and that's how a laser operates. You're working at what wavelength did I give you? This is at lambda equals helium neon, 632 nanometers. It's red. Okay. So one of the neat things about the lasers is they have a very high Q in terms that they're operating at a high frequency, 474 terahertz, and it's got a line width of maybe a few megahertz, and so that ratio is dramatic. It's 10 to the 8th. So it's a very impressive number, and it sounds impressive. And the major reason is because there's a lot of waves, a lot of wavelengths stored in here. There's going to be something on the order of millions of waves in this thing. So that's why the Q is so high. We're just storing so much. Your simple LC circuit, it is the wave. It's a bulk circuit. It doesn't have lots and lots of room for storage. So this is just storing just tons of energy, and that's why the Q in that can be quite so high. But it's an impressive number. Yes?
That 99.8, that is 7-inch LC.
Yeah, this would be my percent reflector. So there's a little bit of light leaking out here, a lot of light leaking out there. But the numbers sound impressive, and I just want to mention that. Let's be realistic though. When I compare this to an RLC circuit, the RLC circuit has one resonance, whatever it is, square root of one over LC, so I forgot what it is. So you've got your resonance, and then you got your half width. And if I go up in high frequency, it doesn't transmit. If I go below, it doesn't transmit. It's only going to be transmitting at that one thing. It's got one resonance. The cavity has a lot of resonances, and we just talked about that. If we looked at this thing in terms of frequency space, here's frequency, here's 0. If I had a laser operating at 474 terahertz, and there was one transmission peak there, then I would literally have a Q of 3 times 10 to the 8th. But in fact, I also have a resonance here, and here, and here, and here, and here. I have lots of resonances. So to say, yeah, it's going to knock out all but 1 part in 3 to the 8th is not quite fair, because it's going to let some other guys through in adjacent places. And in fact, every FSR, there's an allowed mode. So the Q is an interesting number, but it's not something it's not fair to directly compare it to an RLC circuit. So what is a better fair comparison is to kind of zoom in on this, and you say, well, if I really look closely at the frequency space, oh man, here's my axis, here's my Qth mode, and I've got this mode running, and I really like it. I got a small line width, and I'm cool with that. But over here, here's Q minus 1, and here's Q plus 1, and here's my free spectral range, and here's my free spectral range. And so this free spectral range means what's the range over which there's no other interference. That's what the free spectral range means. So I've only got a zone here before another one kicks in. So basically we say, we're going to give you one FSR and say, you're the only resonance within one FSR. And so we're going to define a modified Q called the Finesse. You've probably heard the word Finesse. We define it formally. So yet another definition today, Finesse. And it's the free spectral range divided by delta nu 1/2. So instead of being nu, the absolute frequency divided by the half width, it's the free spectral range divided by the half width. And this is a much more realistic number. You put numbers in, you do the math, and it turns out to a formula like this: pi r1 r2 to the 1/4 divided by 1 minus R1 R2 to the 1/2. The example I just gave you right there, this has a finesse F equal to 117. So, okay, that's a Q that's kind of like when I see an RLC circuit. Okay, I got a Q of 100, whatever, yeah. So this is okay. So this is typically the number we use to characterize a cavity. What's the finesse? In other words, how much, what this tells me is it'll knock out all, 116 parts out of 117 will be knocked out, and only that 1 and 117 will be let through filtered in terms of spectral components as a filter goes. So, yet another term. This is one you want to remember when you use an etalon or something like that. We'll say, what's the finesse of the etalon? Q, it's good to know about. Yeah.
Shouldn't the finesse be dependent on D somehow?
Well, it's dependent on D only in terms of the C over 2L. It's there, but it doesn't. If I make the cavity longer, I don't improve the finesse. Finesse entirely depends on the mirrors. So, okay, let's talk about photon lifetime. I want to get to one more formula. I can be just short here. Photon lifetime is real simple. And we talked about the buildup of this cavity, this thing up here. You can compute this on the back of an envelope at lunch today. So it's nothing magic about this. Imagine you got a cavity. It's got some reflectivities. You got a blob of photons here. Just take a blob of photons. Let's say there's N of them. Let them go around the cavity once. How many remain after one round trip? So I started with N. I go here, I reflect. I'm only going to have R1 times N left. So R is less than 1. I come back to here. I'm going to have R2, R1N. And then I'm back to where I started. So in one round trip, I went from the N photons to 1 minus R1, R2 N photons. So I've got a dN. I want to calculate dN dt. How fast are these leaving? So what was my time? How long did it take to do a round trip? So I know the length. I know the speed of light. So turns out if this has a distance d, then it's 2L over C, or 2D over C. It's 1 over the FSR, it turns out. So it's just the distance I traveled divided by the velocity gives me the time. So I can quickly put together a dN, here's delta n, equals 1 minus R1, R2 n, and a delta t is just 2d over c. So I've got a differential equation. dN dt equals all this crap times n, and I can solve it. So what you get for that is you get a photon lifetime. You get a differential equation, and you're going to find that n of t goes as e to the minus t over tau, and tau photon, I love photon lifetime, it sounds so sexy, it's just really just the leakage rate, is, and you can do this yourself, 2d over c, 1 over 1 minus R1, R2. If you can read that, I'll be impressed. So, this is the photon light. I'm kind of rushing there. There's one more formula I wanted to get to. That's just photon life. So that's how long it takes to build up the field inside this cavity, and that's how long it takes for it to decay away. So we will talk about, that tells you kind of how fast a cavity can respond to a change. We'll find when we talk about Q switching or relaxation oscillations, this kind of plays a role. But your cavity, it's a big stored energy system, and how fast can you perturb it? That's as fast as you can go. Okay, the last equation I wanted to get to. I told you when I started the lecture is that every one of these modes had a different frequency. Now, how do we figure out the frequency of a specific mode? So we wrote down the equation for the Gaussian. I'm just going to write a little bit of it. We knew the electric field is a function of x, y, z. It goes to some E naught. We had omega over omega of z. And then we had the Hermite polynomial thing. Just put that one of x. We got a Hermite function of y, and then we had the Gaussian. Now, I'm not going to write all that down, but I'm going to put in the phase term. We have phase term e to the j k z, and then this phase term gets modified when you add the Hermites. Remember what it was? Kz, remember what it was? Kz minus what? Or plus what? It was, you said it? It was tan of z naught, or tan inverse of z over z naught. It was that crazy little p of z function. Let's get modified. And this becomes 1 over pi times m, well, oh, I'm jumping ahead. It becomes minus m plus n plus 1 times tan inverse of z over z naught. So this longitudinal phase from that p of z thing shows up again. And depending on the Hermites, you get a little bit of difference here. What's the frequency of this? When this thing here equals 2 pi times some integer, that's the frequency of the mode. And you can see the frequency is going to depend a little bit on the Hermite numbers here. And so when you actually write it, when you convert that into frequency of the NMQ mode is this formula, C over 2L times Q plus 1 over pi M plus N plus 1, and I'm going to do it in terms of G, cos inverse of square root of G1, G2. Okay, so this is the actual frequency of every particular mode. There's nothing magic here. The only thing we did was when we looked at the solution for the Gaussian beam, we had to modify the phase term here. But what that does is it makes every mode have just a slightly different frequency. And so if I go and look at all the modes in a cavity, and this is my last 20 seconds, I'm going to find I have a mode every FSR. So here's Q, Q minus 1. These are separated by FSRs. This will be the mode for the 0, 0. So I take my TEM00 mode, and it's going to have every FSR in allowed mode. Now if I go to the 0, 1 mode, it's going to be sitting right about, maybe it depends on what all these terms are, it might be sitting right about here. And the next 0, 1 mode will be right here, and the next one will be right here, and so forth. So they're separated by an FSR among themselves, but they're offset compared to the other mode. And a 0, 2 might be, you know, here, and a 4, 4 might be over here. You know, who knows where they are. But they go all over the place. So every spatial mode has a slightly different frequency than the 0, 0, and from each other, in fact. So that's why when you're running multi-mode lasers, you lose the spatial coherence because every mode is changing phase at different rates. Yeah.
What are those inside the cosine there?
Oh, G1 and G2. Do you remember we talked about this? G. Remember we did that stability diagram thing? And G, we defined G as 1 minus, what was it, L over R, say R2. So this is our stability terms. That's where that comes from. Now, of course, if I have more than 2 curved mirrors, G gets kind of weird. So I'll have to show you the G formula. But that's what that, it's in terms of that. So those are those resonance of the cavities. So that's what I wanted to get across. I want to get that formula. I went way overdue. Sorry.